So we're looking for the area under this curve. Any ideas? Like the other one, we were very simply able to break it into simple shapes. This one, not so easy, is it? Yeah. Okay, and that's where the ideas of some pretty smart people come into play. So let's see what we're doing here. Oh, there's the tangent. Oh, the memories, tangent lines. Yes. Okay, so oh, I froze it here. We're looking for the area under that curve, and at this point, if you want to open your packets, now's a good time to do it. So if you have see your Apple Pencil is leaning, that's leans, inspirational. Okay, well, someone may look at that and say, well, it's kind of hard to get the area under this amorphous kind of shape, but I could break it up into simpler shapes and get some approximations. One of the simpler shapes is rectangles. So what we do first is say I could break up our region into two pieces and just make rectangles for my approximation. I want you to notice for this diagram here, the heights of each rectangle is defined by the left side of each interval. Do you see that happening with the red going up, making the height of the rectangle? Let's look at the base of the rectangle. Does this expression here make sense? B minus A over 2. B minus A comes from the fact that we're starting at A and going to B, so the full length is B minus A, and then this particular instance is being divided into two pieces. Now, is this a pretty good estimation of the area under the curve? Comparing that to that, what do you think? That's a pretty bad approximation, don't you think? But it's something. Is this an under approximation or an over approximation? It looks like an under approximation for sure. And we could get a more accurate approximation if we divide it into more rectangles. And like this one is divided into 4. And in this case, you can see each base. Do these expressions make sense at the bottom? Yeah. Each one has a length of B minus A over 4. And in this case, it's arbitrary that the person who made this example has chosen for each interval to follow the right side of each one to define the height of the rectangle. As opposed to this one over here, like here, that this first one is defined by the left side of the interval. In this other one, they just said, okay, my first rectangle is going to be this high. My second rectangle is going to be this high. I'll always come from the right side of each interval. And which one's better? Second. Well, definitely this is a better approximation. In this case, we have an over approximation, apparently. But neither one's really good. And in terms of whether you choose left or right points of the interval to define the height of the rectangle, it doesn't really matter. It's more what the question's asking you. Choose the left point or the right point, and you'll see what I mean in just a moment. But you can see that if I were to make, instead of 4 rectangles, we made 8 rectangles or 100 rectangles, we'd be getting a better and better approximation, don't you think? So we'd just be dividing into more rectangles until they become close to the area of the region under the graph. Now, could we ever actually get the area of the region under the graph this way? Well, there's a tool that we've been studying recently, isn't there? Limits. What would be taking the limit of? The number of rectangles approaching infinity. If we could find that the limit, then we would be getting the actual area under the curves. And that is a second part of calculus. So this is just kind of a window into the idea behind the second part of calculus. One of 2 big ideas. Okay, let's try some examples here. I don't like the examples that they've given us. I'm going to cross this out. And let's say we're going to start with 1/2 x squared plus 1. So let f of x equal 1/2 x squared plus 1. I don't want to go from 1 to 2. I want to go from 1 to 5. So we're going to partition the interval 1 to 5 into 2 subintervals of equal width and use the right endpoints of the subintervals as heights to approximate the area under the curve. Is this estimate an underestimate or an overestimate? For this one, we're going to start by graphing. Hope you're okay graphing that function. Rohan, you okay with that one? I'll tell your Algebra 1 teacher. It's a good job. Okay, so you have something like this. Something like this, and we're going from 1 to 5. So here, actually, I'm not going to draw anything. Please follow the examples or follow the prompts and do what it says. So you're going to draw it first. Draw the rectangles. Check it with your neighbor once you've drawn them, or you have no idea what to do. Check it with your neighbor. How many tick marks do you put between 1 and 5? Just one, because we're breaking up into 2 pieces. And for each subinterval, we're traveling up the left side or the right side. And it tells us. It tells us. Use 2 subintervals of equal width and use the right endpoints of the subintervals as heights. So do you see what that means? Like in this first subinterval from, oh no. First subinterval from 1 to 3, we're going to travel up 3. And that's going to be the height of our first rectangle. Do you see how I've drawn it?
So that will be 5. Oh.
Exactly. When we go up from 5, see there, this rectangle. Is this a pretty good approximation for the area under the curve from 1 to 5? It's terrible. It's really bad. But it's a good place to start. Yes, Kieran.
What if we like connected like the top right point of the rectangle to like you made the triangles?
Yeah, that's a thinker. Yeah, I want to talk about that right after we finish with this one. I love it. Don't let me move on without addressing what you just talked about. Thank you. So go ahead and find the area that we're approximating now, please. Did you get it?
Oh.
That is where we're going to start. So 2 times 2 times.
3.
I plug in the 3.
What?
11 over 2. Right, so what we just did is in our heads, or maybe not in your head, I don't know, you plugged in the 3 and you got this, you got 9 over 2 plus 1, which is 11 over 2. So that height of the rectangle is 11 over 2. Why am I multiplying by 2? Because that's the length of the base. I'm just finding the area of a rectangle. So I'm going to take that and add to it. 2 times Is 27/2?
Oh,
Any questions? Is this an over approximation or under approximation? For sure,
Yeah,
over
I'm
approximation.
quite confused.
Uh-oh, what's wrong?
Yeah, originally, I multiplied it by like, but how'd you get the height? How'd you get the height?
plug it in.
You just plug it in?
Plug it in.
Yeah, this right here is f of 5.
Okay.
This is f of 3. Do I care about f of 1? Not in a cold-hearted way, but it has nothing to do with any of the rectangles. So we're just gonna leave it alone. If we would have been doing heights defined by the left endpoint of each interval, then it was ended up f of 1 and f of 3, and then left f5 alone. That's what you need to do. Now, Karen, you asked a great question, and if we're really trying to approximate the area, you notice that this is a terrible way, isn't it? And Karen,
Yes.
your recommendation was to do what?
Like, see the triangles at the top.
Yeah, why even split this? Just like, kind of like this, maybe?
I mean, I was thinking something else.
Or you think something else?
Sure, yeah, you could do that.
Like, this is one way of approximating, and this shape is called
Trapezoid.
a trapezoid. Or if we have the subintervals, maybe this is what you're thinking. Maybe you could do this, like you could
Yeah,
make
something
these
like
trapezoids,
Yeah.
and that's actually a really nice approximation, isn't it?
Right, yeah.
And then this is trapezoidal approximation. It's something you'll work on next year, but today we're keeping it simple and just doing the rectangles. But thank you for bringing up that. Why use rectangles? It's kind of arbitrary.
Right.
Yeah, so thank you. Anyway, I'll take this back to the rectangles. Okay, let's move on to next. Shall we try another?
We shall.
Let's do it. 2x. I'm just trying to cross that out. That's not an x. Let's do something fun.
Oh. Why is that necessary?
What? What just happened? And we're not going to go from 1 to 2. We're going to go from 2 to 11 and cut it into 3 sub intervals. So I'll keep the rest the same though.
Well, yeah, under the curve,
Does that include
wouldn't
the
that make it
negative
like?
numbers?
Oh, going down to the x-axis.
Oh.
Good
Oh,
question.
okay, perfect.
Otherwise, it's just infinity.
Do you want us to do rectangles?
Yes, this is rectangles. Right, it doesn't specify that, does it? Rectangle space. You want to use your calculator for this. So let's round to the nearest 1,000. So you'll definitely want to use your calculator. Did you get it? Do you remember what the function even looks like?
Yeah.
It has a what intercept?
uh,
X-intercept of
One was.
1. Better have that on yours.
I do have that.
No surprise. Also crosses to the points. 10, 1. Ooh, 100, comma 2.
1,000.
And 1/10, comma.
Billion. 9.
Ooh, pretty hot in here.
Do it again, do it again.
Trillion.
Does yours go up to a billion?
Trillion.
I should go up to Google.
12.
Google one.
Okay. So looks exactly like this. We know this is a 1 right here. We're going from 2 up to 11. There are 3 subintervals. So how big is each one? How do we get that 3?
2 minus 11.
11 minus 2
Yeah, divided by 3.
is 9. Divide that by 3, we get 3. So this is 2, 5, 8, and 11. Are we good with those? And then from there, we're just making rectangles that are defined, whose heights are defined by the left side. By the height of the first one is exactly log of 2, isn't it? Height of the first rectangle and the second one. Log of 5, log of 8. And that's the last rectangle. So if I want to get in my approximation, the area is approximately equal to 3 times log of 2 plus 3 times log of 5 plus 3 times log of 8. Mind if I factor out the log? I'll take that as a number stream, but that's fine. We could, this is interesting, we could use our properties of logs to make this a single log, can't we? Log of 80, right? That's kind of fun. But let's, I just want to take this opportunity to show you something on the calculator. Let's see. Okay, there we are. So if I want these values quickly, now it's easy to find log of 2, log of 5, and log of 8. Is that the ones we were doing?
Yeah.
I'm gonna use my calculator for that though. So log x. And I could go to the table. Like I think before it was at we were choosing the x's, but I want the calculator to do everything for me. So what I'm gonna do is I'm gonna have my table start at 2. And have my delta table be
11.
9.
9.
3. And I want the independent to be automatic. Does that make sense? I'm telling you exactly what I want in the table. Starting at 2, so this is gonna give me 2, 5, 8, 11, etc. So when I go to my table now, I have all those values waiting for me. I think you already had those in your calculator when you were doing these.
Yeah.
Does that make any sense? It's just a function, like a way you could use your calculator, take control of that table. Of course, if you just kept it in ask, it's not difficult. Just put in your 2, 5, and 8, just get the same thing. It does all of them. Just kind of nice. Okay. Back to the regularly scheduled programming. Here we are. Oh, so what was the approximation? When 3 decimal places?
5.71.
5.709.
Yeah.
Yay. Over approximation or under approximation?
Under.
Under approximation. Cool. I'm not going to do example 3 because that's kind of how we started. It's giving us a very simple function than just saying to find the area from 1 to 2, like to actually find that area. You notice, of course, the shape. Trapezoid, you should be able to find the area under there. So I'm not going to go over that. But I do want to take you a little bit deeper into the Mathemese portion of this class. So don't write anything down yet. Just kind of put your pencils down and give it a listen. I'm going to generalize what we just did. We are finding the area under some function f of x. So here is f of x. From an interval a to b. Given that that is a to b. I'm going to divide this into a bunch of triangles. I don't want to nail down any particular number. I don't want to say 5 or 10. I definitely don't want to draw 100. So I'm just going to divide this into n number of rectangles. So I'm going to start with this. So I'm going from A to B, and I'll remember that this is A and this is B down here. I'm going to call this x sub 1 just to have some continuity. I'm going to call this one x sub 2. This one is x sub 3. And this last one is going to be x sub n. Now I'm going to be using left hand points to define the height of each rectangle. So here are my rectangles. I'll draw the first 3 and then I'll draw the last one. There we go. And I'll put a dot, dot, dot in here. So to define the area, let's talk about my delta x. What's that little delta x length? Oh, I'm going to use the numbers that they gave us to start with. I'm going to say b minus a over n. Because based on the number of rectangles I have, the x values could change. X1 won't change, but all the other ones will change. So I'll start with b minus a. That won't change. B and a will change. N will change, but we'll deal with that when we come to it. And I need the height of the rectangles. The height of each rectangle is f of x sub n, isn't it? So now if I put these together, okay, so the area, and I'll give you a chance to write this down in just a moment, and leave a space right here. I'm going to take, since they all have the same base, I'm going to factor that out. And this leaves us with f of x sub 1 plus f of x sub 2 plus f of x sub 3 plus dot, dot, dot plus f of x sub n. Are we good with that being the sum of all the rectangles? And I'm trying to think in my toolbox, is there a way to consolidate this right here? Yeah, let's use some summation notation for that. So b minus a over n. Got that sigma going, and now it's going to be f of x sub. I'm going to use k here, and k is going to start with 1 and go up to n. So this represents all the rectangles, and now I'm going to use our new tool from this unit, not this section, but this unit, and take the limit as
Expression B.
what approaches what?
Expression A.
It's n approaches infinity, right? Because n is the number of rectangles I'm dividing. And I want there to be an infinite number of those rectangles. Each one, how thin is it going to be?
Infinite.
Infinitesimally thin. So the area is actually equal to this. And I'll put this up here. On this limit as n approaches infinity. I'll give you a minute to write this down and we can catch up if you like to do that. Read it okay? If you're worried about what you have to know for the test, you don't have to memorize this for the test. You have to know the idea, the rectangles, but that's about it.
What about on the quiz?
On today's quiz,
Yeah. No.
yeah,
Hey, you never know.
the day's material is never on the quiz. But it's a good question. Almost done with this, so if you haven't finished, you'll have time to catch up to writing in just a second. But last time we talked about derivatives. This is the second big topic in calculus. Do you know what this is leading up to? Integrals. Yeah, this is by definition what's called an integral. And the symbol for an integral, you know what it looks like? Okay.
Italicized.
Have you seen that?
Yeah.
It's an elongated S. It's elongated S because it comes from the sum of an infinite number of things. So this right here basically becomes this. So you're going to see integral of f of x. There's going to be a lower and an upper bound for that integral. They're written here next to the integral. That just means we're going from A to B. And I still need to do that b minus a over n. That is called a differential, x differential. So when you see this integral, you're thinking, oh, this is the sum of an infinite number of rectangles, the base of which is infinitely or infinitesimally small, the height of which is the height of the function. Any questions?
It's the EX in the first part of it.
Yeah, the dx comes from this. This is our delta x. Delta x is like something you can see. Delta x is infinitesimal. But again, I'm just introducing, again, you don't have to know this. There's not going to be a thing that I'm going to test you on, it's introduction. You do have to know how to add up rectangles, so. Yes,
So what's the logic of like knowing that the area is equal to?
what is the logic?
Yeah.
Well, the task at hand was to find the area under the curve. So that's what we're doing with it, saying, oh, these rectangles aren't exactly it. But if I have an infinite number of rectangles, that is the area. Good question. It's important to have the big picture there, so thank you. So we're gonna do one last problem. And this is gonna be a calculator problem. Find the area under the curve. Let's do this one. F of x equals log of x from 2 to 11. Let's see how close we were. So to do that, we are going to use our calculators. What function are you going to look for in your calculator?
Integral.
Integral. Let's see if you can find the integral without me. I bet you could.
Quinn already found it.
Hey,
Oh,
Wow,
wow.
spectate.
How did you do that?
yeah, there's math 9. And where else is there? There's one other place.
Gonna be like 5.9.
It's really.
Over under 5.8. Wrong. Over under 5.8.
I think it's gonna. I think it's gonna be. I think it's gonna be over 5.5.
Yeah, over. Over.
Is it-
Did you find the other place where you can find integral? Alpha F2.
Okay, now my regular.
Remember Richard when you talk, right?
When I click 9, it's you.
You got it. You like that.
Wait, we don't know how many.
No, but like really.
What's going on?
You should ask.
Ah, there it is.
That's right, actually. That's fine.
Okay, so I went alpha window for. Okay, so what's at the bottom of this integral? The top, 11. Inside here is going to be log of x. This is our function. Log of x, and then d x, because it could be dy, it could be small y's, but usually it's x. And we hit enter. Are we close in our approximation?
No. You're not.
Not so close, but we were correct when we said it's an under approximation.
Yep.
But it was quite an under approximation, wasn't it? That's okay. Any questions? Okay, I can give you a couple minutes to piece these back together. I'll put the notes back up here. Copy anything. And we'll start the quiz. Not that one. Back up. So in just a couple minutes. At 33, we'll start at 33, so 4.5 minutes or so.
We're gonna do this later.
Okay. I'll give you 17. 17. Pretty short. Most people will give up. Like, I just want to struggle too much.
Four, one goes one way and one.
How many questions is it?
Oh,
So because you know.
9,871.
No, right.
You'll see. That's them.
Both sides voting, would that be?
Wait, this is
Like,
alternate.
if it's contradictory still.
Infinity is involved.
That's.
What about law?
That's how you. And it's-
Well, for what? One, three, 17. Okay. Yeah.
Thank you.